Okay, so the ideal characteristics of an op-amp, if I redraw the symbol, it's probably helpful. So this is our output, and these are our inputs, non-inverting and inverting inputs, and this is our positive power supply and negative power supply. So the ideal characteristics of an op-amp are where, let's have a look at the inputs first. The input impedance is infinity. Now what does that mean? What does the input impedance means? It really means that the current flowing either into or out of the either input is zero. Okay, so the reason why we wanted to have an input impedance of an infinite input impedance is so that if I have a voltage divider connected to one of these, then we don't get current flowing into or out of the voltage divider, and so it doesn't affect that input voltage on the pin here. Okay, and so this current into or out of either of these pins is zero. Okay, so that's one of the ideal characteristics of an op-amp. Another is that the output impedance is zero. And in the same way that if we have an infinite input impedance, it basically, think of input impedance as being an opposition to the current flow. If we have an infinite impedance, an infinite opposition to the current flow, we don't get any current. If we have zero opposition to the current flow, it means that it provides as much current as is needed. Okay, so the output current is not limited by the op-amp. Okay, so my out could be anything it needs to be. So I could power an LED, so switch an LED with one of these, or I could power a motor or a relay or anything I like for an ideal op-amp. In practice though, very few op-amps do have a zero output impedance. Some have very low output impedance, and way you can tell whether the output impedance of an op-amp is relatively low or not is by when you actually draw a current on it, do you measure much of a difference between the output voltage and this supply voltage. So you might have noticed when you're doing your experiments that when you had an LED on the LM741, the output voltage, with a supply voltage of about 9 volts, the output voltage may be 6 or 7 volts. But when you took that LED off and had no output current there, then that output voltage jumped up to about 8 or 8 and a bit volts. And so what you're seeing is the effect of the output impedance reducing that output voltage when there's a current flowing through it. Okay. The other one that we want to know about and prefer to have, now this isn't really something that's easy to measure, but it's stability with negative feedback. Okay, so I was explaining this to somebody earlier about how way you might be able to picture this. Let's say with negative feedback, it's the same sort of idea as, say, if you're driving your car along a slippery road and your back wheels start to slide out a little bit. What you're going to do is trying to turn the wheels such that you want to reduce the difference between the angle that your car is and the angle that you want it to be. So you're trying to reduce the difference between what your actual current angle is and what you want it to be by doing some action that has a negative effect on, so turning into the corner, for example, okay, or turning into the slide. If you did that perfectly, you would slide out and then you would sort of straighten up again and keep going. Okay, so if you did that perfectly, there would be no, you would get back to the direction you want to travel without any trouble at all. If, however, you overshot it, so you didn't do it perfectly, and you started to go the opposite direction, then what you would do is you would go, oh, okay, change the other direction, turn into the other direction to slide, and so what you're going to be doing is going from one side to the other. And if you keep overshooting it, that's right, you're doing this. You're going left and then right and left and then right and zigzagging and doing a slide that looks like this as you're going along. Okay? That is a problem with stability. What it means is that your negative input you're putting into your steering wheel, into your system, is overcompensating for the amount of difference that you need to overcome. And so you overshoot it each time. Okay? And with an amplifier, it's really no different. When you have negative feedback, what it's trying to do is it's trying to change the output to be the desired output, but if it overshoots it, then what it's going to do is it's going to have the output and it's going to be doing this. Okay? Even with a steady input. Okay, so you can have no difference on the inputs here. So your input signal is steady and constant, but your output is actually changing a lot. Okay, that is a symptom of a system of an amplifier that has poor stability. Okay, and for an audio amplifier that can be very bad because you might be able to hear it. Okay, so if this oscillation is in an audible range, then you might be able to hear it. Or likewise, if you've got a radio transmitter or something like that, or a radio receiver, it might be in a range that affects the signal that you're actually trying to send or receive, and be added to or subtracted from that signal you're trying to receive, which would be a problem. You don't want that. Okay, so these are the ideal characteristics. Effectively, we've got no current flowing into or out of the inputs. There is no limitation to the current into or out of the output, and it doesn't, under a steady signal or a steady input, we don't have an oscillating output. Okay. Okay, so the next one that we're going to look at now is the comparator, and then we're going to look at it under a special condition where we call it positive feedback. We covered the comparator the other day. That was where we had an op-amp, and it doesn't matter which order the plus and minus goes, by the way. I can draw it either way I like. And let's say we're having a circuit that's measuring temperature. And so let's put a thermistor here. Okay, and well, let's put a switch here. Let's put a solenoid here that's turning an oven on and off. Okay, so that's a symbol for a solenoid. It's basically an electromechanical switch. So it's actually a mechanical switch, but it is controlled by an electromagnet. And so I can switch on or off this mechanical switch with a current, basically. And usually you use a solenoid for high current switching. So if you're switching, well, an oven, for example, or a motor or something like that, generally use a solenoid because a transistor or a MOSFET quite often can't quite handle the current or the voltage characteristics that is required. Okay. Also, a MOSFET is a DC kind of device, so it only handles current one direction, whereas this is just a switch, so I can switch an AC load without having to worry about the kind of circuit or semiconductors. Okay. Okay, so here is a simple comparator circuit where if I were to increase the voltage on this point here compared to this point, it's going to eventually saturate high and turn on my solenoid. Okay, so if I were to have this set up so that as the temperature decreased, then this resistance here grew. Eventually the voltage across this would get enough to be equal to or greater than this one, which would make the comparator saturate high. Now, an example, actually, who can remember how can I make this so that I can actually control or calibrate the temperature at which I want it to switch on and off at? Anyone remember how to do that? That's right, make any one of these a variable resistor. So that one, doesn't matter which one, but I can make that one a variable resistor so I can adjust this voltage here, which we call it the reference voltage. I can adjust that reference voltage up or down as I want to change how this thing, the temperature at which this thing will switch on or off at. Okay, who can think of a problem with might happen with this? Let's say it warms up, and so it turns off when it gets to the temperature that you've set it to, let's say 100 degrees. So we want our oven to be sitting at 100 degrees, so I set this so that it's set to be 100 degrees. As soon as it gets to 100 degrees, it's going to turn off. Okay? And then it starts to cool down again, yeah? As it's cooling, and the hot things cool down. And so then once it gets below 100 degrees, it turns back on again. Then turns back off again, back on again, back off again, back on again. It's going to do that reasonably quickly. Like it might do it once a second or so. Okay? But these mechanical switches, they wear out. We don't want that. We don't want to be operating that switch lots and lots and lots, because it's going to make the switch wear out after not as much time as we want. So how do you think I can make it so that it takes a little bit longer to turn back on again? So basically what I'm saying here is that the turn on temperature is higher, sorry, the turn on temperature is lower than the turn off temperature. So it turns off and then it cools down, let's say it cools down by 5 degrees, so not half a degree, by 5 degrees before it turns back on again. And then it takes a little while for it to warm back up again before it turns back off again. Okay, so how can I change? Well, what is that phenomenon called where the temperature, or there's a difference between the turn on and turn off? We looked at it in a digital unit on Schmidt triggers. So what was that phenomenon called? Hysteresis. Hysteresis, isn't it? Okay, so hysteresis would look something like this. Right, so the definition of hysteresis is if we have 2 points A and B, and it doesn't actually matter what was on the axis here, let's say temperature and output voltage, then as I increase my temperature, the output voltage drops. Okay, so I'm going in this direction, and then it drops. And then it doesn't matter if I keep increasing my temperature, it's still the output's going to be off, all right? But when it starts to cool back down again, it doesn't go back this way, it follows this other direction, this other pathway, okay? And so the pathway from A to B is different than the pathway from B back to A again. That's the definition of hysteresis. Okay, so this is kind of what we want. We want a hysteresis effect. And so this might be temperature, and this is the output voltage. So this is the kind of thing we're after. Now, what we can do to change this is muck around with this reference voltage. We'll muck around with this signal voltage. It doesn't matter which one. And we can make it so that this, let's put the non-inverting one, be the one that we're changing. If we make it so that this voltage here is determined by the output to some degree, then this voltage here is what needs to change a bit more. So I think what I might do is change this around just a little bit. I'm going to make that the non-inverting and that the inverting. Okay? It doesn't actually matter. It still works, but I think it might be easier. I might also make that one my regular resistor and that one my variable resistor. The only reason I want to do this is because I want to make it so that I'm reducing as many different things or variables as possible. Okay? So the only thing I want to know about here is R1 and R2. So what I can do is I can change this voltage here, which is going to be my reference voltage. I can make that voltage there change when the output changes. So if the output is high, it's going to have a different reference voltage to when the output is low. Okay? And the way I do that is by connecting a resistor between the output and that non-inverting input. Okay? So it has to be the non-inverting input. Right? If I put on the inverting input, it has a different effect, which we'll look at when we look at amplifiers. And so if I have it on a non-inverting input there, that changes the output voltage based on what the changes what this reference voltage here is based on what the output is doing. So if the output is high, it's going to have a higher voltage on this reference point than if the output is low. You can sort of think of it, okay, well it's connected to there, so if that's high, it's got to make it higher. If it's low, it's got to make it lower. But let's actually dissect that and see what it looks like on a simplified level without all of this op-amp stuff in the way. We can sort of think as the op-amp output here as being a switch that's connecting it either to the positive or to the zero, the negative side. So let's draw it like that. So I'm just looking at the voltage divider now. And let's make it 9 volts just because. And basically what I'm saying here is my resistor. And this is connected to the output of my op-amp. Now remember the op-amp, when it's connected like that, it's either going to be saturated high or saturated low. So it's either going to be saturated low, so connected to 0 volts, or saturated high, so it's connecting it to 9 volts. So basically what I've got here is a switch that can switch between either connected to saturated low or to saturated high. All right. If I redraw this into 2 different cases in a way that might make it really clear. So this is when it's saturated high. The switch is drawn as I've shown it now, so it's not connected to 0 at all. This resistor here is connected to the positive. Okay? So I've got R1, R2. Now I'm going to call this RF, F for feedback. Alright, so what I really have is both of these 2 resistors, R1 and RF, in parallel. Okay, so when they're in parallel, that's going to give an equivalent resistance of this. And is that equivalent resistance going to be smaller or bigger? Parallel resistance, you've got more pathways for the current to flow, so there's got to be less opposition overall to the current. So it's going to be a smaller overall resistance. Okay, so that's the same as a single resistor, which is less than R1. Okay, so equivalent, which is going to be less than that R1, which is what we have here. Okay, and so compare the 2 voltage dividers that we had, just R1 on its own, and now I've got a resistor here that is smaller than that. What's that going to do to this output voltage here? Does it go up or down? It goes up, doesn't it? Right? You can sort of think of it like this way. If that resistor is smaller, this point becomes better connected to this point here. Alright? Better connection, bigger voltage. Okay? So we're closer to this voltage. Alright? So if I have this feedback resistor in, when the output is saturated high, it's as if we've got it like this. If we've got a simple circuit made up of 3 resistors connected like this, and this reference voltage here, which is really what we're looking at, is going to be, actually that should be that goes to the non-inverting input, doesn't it? Okay, of our op-amp. And so that voltage there, which we're calling our reference voltage, is going to be greater than it was without this feedback resistance. Okay. Now look at it with a saturated low instead. Okay, so that's as if we're now connected with our switch like this. Okay, and instead of having the resistor in parallel with R1, this feedback resistor now is in parallel with R2. So it's nearly the same. Okay, and so now it's almost the same as it was before, except we've got an equivalent resistance which is less than 2 now. This resistance is smaller than it was. So what is this reference voltage going to do? Is it going to be bigger or smaller than it was before? It's going to be smaller, isn't it? And so this reference voltage here is now lower. Okay, and so what we're seeing here is when it's saturated high, the reference voltage was here. So if this was voltage now, so the reference voltage on our, actually no, this is the, it's got to be in, because that's what we've been doing. So that's the input voltage on the non-inverting input here. And this voltage here, where it switches, is now higher than the voltage, so this is where it switches off. And it's higher than when it switches back on again. Okay? And so that's how we can get our hysteresis effect, by connecting the non-inverting input to this to the output with a feedback resistor. Okay, so any feedback, well, feedback is where we're feeding back some of the output back into the input in some way. So whether it's connected to the negative or the positive, it's still going to be a feedback effect. But for this hysteresis, what we need is to have that feedback be onto the non-inverting input, so the positive input there. Okay? If we have it connected to the negative input, what we actually do is change, we still get a hysteresis, but it won't work because it changes it at this point. Okay? And so you actually never get to it. It doesn't work. Alright? So if we have that on the inverting input instead of the non-inverting, we won't get the hysteresis effect that we're after. We end up with, because what happens here is as soon as it turns on, turns off, it's able to turn back on again. Okay? So it's not going to work. And so what we need to do is have it on the non-inverting input.